So I really hope you found the last video at least somewhat exciting, because it shows you the logarithms actually do have some value in the mathematical world. Like, they're not just these annoying things we don't know how to do. Turns out when derivatives are involved, logarithms are actually awesome because they can significantly decrease the complexity of a problem. So what you effectively saw in the last video is that when a function has a natural log, its derivative will probably be fairly easy to do because you can break it down. So what about problems that don't have natural logs? Like, are we just stuck there? And the answer is not really. We can inject the logarithms into a problem to make it easier, and that's what this process of logarithmic differentiation is all about. But in order for us to get that, I really have to first do a review of implicit differentiation to remind you of what that is. So I'm going to go through an example of that, and then we'll get to the new thing. So the first thing I'm going to do is this review of implicit differentiation, right? So I'm going to ask you to find dy dx. Find dy dx if the natural log of y is equal to x cubed minus 3xy. Actually, I'm going to do 3xy squared. So the whole idea on implicit differentiation was that you've got a function that doesn't just say y equals and you want to take the derivative. And the way we do it is we just walk through the problem and we just go from left to right, the derivative of each thing. And we remember, any time we take the derivative of something that's not the bottom variable, we have to write d whatever d that, right? So for instance, let's just walk through this, right? First of all, the derivative of natural log y is 1 over y. Now, chain rule, the thing that was inside was a y. The derivative of that is dy dx equals the next thing, x cubed. X cubed just involves x, so its derivative is simple. That's just 3x squared. Even if you wanted to do the chain rule, it would be times dx dx, whatever, times 1. I'm not even going to write it down, right? So now the next thing, now I need to do the derivative of minus 3x y squared, right? So that's a product rule. There's a minus 3x and there's a y squared. So I'm going to do the derivative of the first one, that's minus 3, and leave the second thing alone, y squared, right? Then plus, this time I'm going to leave the first thing alone, that's negative 3x, and I'm going to multiply by the derivative of the second one. Now that second thing involves a y, which means at some point I'm going to need to do y dx. But first, let's do the derivative of the thing. The derivative of y squared is 2y, then times your dy dx. And at this point, you've taken the derivative. Now we just need to answer the question. The question wanted me to find dy dx, which means I need to move all the dy dx's to one side and all of the not dy dx to the other side. So I'm going to basically move this term to the other side. This gives me 1 over y dy dx. Oops. Dy dx plus, it's going to end up being 6xy dy dx equals the other things that were on this side. This 3x squared minus 3y squared, right? And this is going to get a little bit messy. I'd really like to factor the dy dx's out of these sides, but I kind of don't like the 1 over y being there. So I'm going to multiply the entire problem by a y right now, just to kind of remove that thing from the equation. Dy dx plus 6xy squared dy dx equals 3x squared y minus 3y squared. And I want to try and keep this video short, so I'm gonna sort of skip a step here. The next thing that would happen is I would take this thing and I would factor dy dx out of it. Once I factor dy dx out of it, I would divide the rest of that stuff over. So what is the rest of the stuff? It's this 1 plus 6xy squared. So I'm going to end up with dy dx equals 3x squared y minus 3y. Just realized I have a mistake up here. I'm sorry. That should be 3y cubed. So 3y cubed all over 1 plus 6xy squared. That is that derivative. And I used implicit differentiation to do it. Right? So now that we're done with that, we can actually get on to the example of what I wanted to talk about. This is really the new thing in this video. I want to talk about logarithmic differentiation. And so how that works is so what if I have a problem where I say find f prime of x if f of x is, and let's say we've got something like the square root of x cubed minus 4 over, over sine x. Right? I mean, there's a terrible problem. Finding the derivative of that thing is going to require the quotient rule. Right? What I'm going to do is I'm going to use logarithmic differentiation. And, sorry, the way logarithmic differentiation works is you start out, a lot of these things you start out by rewriting it with a y just because it's notationally going to make things easier. So it's sort of like I'm saying, okay, my function is y equals, I want us to find dy dx. What I would really like us to do is just find out what dy dx is. Now that I've said that, I'm going to use logarithmic differentiation by taking the natural log of both sides. And I'll write that here in the video. So, using logarithmic differentiation just means that at some point before taking the derivative, you're going to choose to take the natural log of both sides of the equation. And the reason that I'm doing that is I know it's going to let me simplify the problem. So this problem is now the natural log of y equals the natural log of this thing. And now that I've done that, I was going to say I'm ready to take the derivative, but I'm actually not. The whole point is I can now simplify the right side of that thing. I can simplify this into the natural log of y equals the natural log of the square root of x cubed minus 4 minus the natural log of sine x. Right? The quotient rule is now gone. And I can do even more. Like you've seen in the previous videos, this has a square root in it, which means I can pull out that half. Right? This will be natural log y equals 1/2 the natural log of x cubed minus 4. Please make sure that you understand why that happened. If you don't, like pause, rewind, rewatch it. That's probably one of the most common simplifications, is bringing that half down. So there we go. Yay, now it's simplified. Now please note, I have not actually taken a derivative anywhere, right? This is still just the original, this is still just the original function, just rewritten with natural logs, right? I need to take the derivative of this now. So now finally for the derivative. 1 over y times dy dx equals 1/2 times 1 over x cubed minus 4, chain rule, times 3x squared, minus 1 over sine x, chain rule, times cosine x. Right? And yay, we took the derivative. Now all I need to do is simplify that a little bit and then find dy dx. Right? So let's see. I'm going to leave this over here just while I simplify the right side. This will be equal to 3x squared over 2 times x cubed minus 4 minus cosine x over sine x. I could get a common denominator here, but it's not looking very pretty, so I'm going to kind of skip on that. Although I will mention cosine x over sine x, that's cotangent, so I'm going to do that in the next step. So now one of the big things I wanted to do here is I wanted to solve for dy dx, so I need to get rid of this 1 over y. Best way to do that is to multiply both sides by y, and I'm going to end up with dy dx equals y times all of this. Now, I know this isn't a pretty looking derivative, but on the other hand, did we really expect it to be? like if you look at the original problem, if you think about what, where is it? There we go. If you think about what this was going to require to do this problem, like the derivative of that was going to be a quotient rule that had a chain, like a double chain rule built into it. Like it was going to be a mess from the beginning. So we sort of shouldn't be surprised that it doesn't look that great when we finish it. And actually, it's going to get a little bit worse. There's one more step. I hope it's bothering you guys. Like, there's a y here. That's kind of messed up. It would be really nice if that were an x somehow. So it's sort of like, if only there was a way we could change y into x. If only we, somewhere in the problem, had a statement of what y was. You know? Like, if only we knew what y was equal to. You know, if only. Hey, wait a minute. Turns out y is this. So the final thing you can do in the problem, and let's hope I can remember what it was, the final thing we can do is we can write that y is, I think it was the square root of x cubed minus 4 over sine x times all of this stuff that was here before. Now again, I'm not going to pretend that this final answer is nice, but I will say that I don't know, I just don't feel like there was anything terribly complicated about that process. There was no crazy double quotient rule, chain rule thing going on. I understand logarithmic differentiation is kind of a long process, and the final answer is ugly, but it's a nice tool against problems that were already going to be pretty bad from the beginning. Sorry this video was fairly long. I hope that all makes sense, and I hope that you guys will get a chance to start assignment 5.1 just so you know you've got the hang of it before you get to class. But either way, I'll see you there.